So, good evening everyone. Let us start a new topic, that is Fourier transform, that is only useful for the communication system purpose, not for this is not for the basically it is useful for the signal system also, but in this session I cover only those things that is helpful for the communication system. So the new topic is, that is Fourier transform. Okay, so basically the Fourier transform, why do we use the Fourier transform? Because the frequency domain analysis of any signal is easy as compared to time domain signal. So if any signal x of t is given, that is time domain, to know what are the frequency content present in that signal. So so we use Fourier transform to know the what are the frequency content present in that signal, frequency content present in the time domain signal. So we use Fourier transform of the signal. So basically it is used to find the frequency content by the given time domain signal. So the basic formula of so if xt is in time domain signal, so its Fourier transform is x of f. We represent xt in time domain, and frequency domain, this is x of f. So the basic formula of to find the x of f is, that is minus infinite to infinite xt e raised to the power minus j 2 pi f of t dt. Here it is 2. By mistake here it is, I can write another way. So here it is minus j 2 pi f of t dt. So so let's consider a basic signal in time domain. Let us assume xt is a rectangular pulse. Okay, so here xt is a rectangular pulse. I taken as a width of minus tau by 2 to tau by 2 in time domain signal. Here it is a t, and the width of this rectangular pulse is, total width of this rectangular pulse is minus tau by 2 tau by 2, so it is tau, and I take this amplitude as a. So the time domain representation of this signal is simply a rect small t by tau. Okay, so we have to find the Fourier transform of this rectangular pulse. So x of f is simply this thing, this xt we put in that formula. So x of f is, I use a different color, so okay, minus tau by 2 to tau by 2. Between minus tau by 2 tau by 2, xt is a e raised to the power minus j 2 pi ft dt. So a is a constant, so it comes out to integral part, and the integration of exponential is simply minus j 2 pi f of t dt divided by minus j 2 pi f, and you put a limit minus tau by 2 to tau by 2. Okay, after doing this thing, simply put the limit. Okay, if you put the limit here, I write a divided by minus j 2 pi f, and I put limit, upper limit minus lower limit, so e raised to the power minus j 2 pi f. In place of t you put a tau by 2 plus tau by 2, this is 2, minus e raised to the power minus j 2 pi f. In place of t you have to put a minus tau by 2. Okay, so this So this 2 and 2 is cancelled from here to here and from here to here, and after that the things will become a divided by pi f. This one is the pi f, and I simply put 2j between this, so here it comes to 2j, and also I take a minus sign inside, so e raised to the power j pi f tau minus e raised to the power minus j pi f tau. So this is a divided by pi f. This is simply formula of sine. So sine of pi f tau. Okay, so this is the formula of sine pi f tau. So basically I have to convert this function into sinc function. So what you can do, you simply multiply and divide by pi f tau. Pi f tau divided by pi f tau. So this one become a tau sinc f tau. So basically a rect t by tau, it is in time domain signal, so the Fourier transform of this rectangular pulse is sinc. I can do a bit of analysis of sinc function. So basically I do here sinc x is simply sine pi x divided by pi x. So here you can see sine pi x, x is f tau, x is f tau, and you take here f tau. So sine pi f tau divided by pi f tau, this will become sinc f tau, and here pi f and this pi f will be cancelled, and a tau is amplitude. So in that way you return sinc, this expression return into the sinc form. Okay, so the property of the sinc function is sinc x is equal to sine pi x divided by pi x. If there is a sampling function, sampling x is equal to, it's simply sine x divided by x. Here pi didn't come, but here pi comes. So basically, oh, this one is not correct. Okay. We have to plot a straight line. Oh, this will be straight line. Okay. Okay. Okay, so basically the sinc function is looks like in this way. Okay, so this is sinc x. Here it is 0, and you see here at that place I want to tell you one thing, like if I put x is equal to 1, okay, first if you put x is equal to 0, then sin 0 divided by 0. Then sin 0 divided by 0, it become indeterminate form. So what you can do, you simply integrate. You simply not integrate, you simply differentiate upper side and lower side. Like you apply here L'Hospital rule. So if you apply L'Hospital rule, like limit of x tends to 0 sin pi x divided by pi x, then it will become 0 divided by 0. So you apply L'Hospital rule. So after applying L'Hospital rule, you simply differentiate upper side and also differentiate lower side. So differentiation of upper side is limit of x tends to 0 pi cos pi x divided by pi. This pi and this pi will cancel, and apply x and put the limit x tends to 0. So this will become 1. So the magnitude is 1. Okay. And one more thing you have to notice, this x function is always increasing. Like if you put x is equal to 1, 2, 3, so denominator is always increasing. I use a different color. Okay, so denominator is always increasing. But what is the sine function? Sine function is simply switch between -1 to 1. Sin pi x simply switch between -1 to 1. So at 0 you get a maximum amplitude. But after if you after the value of x is increasing, then obviously denominator is always increasing. But this sine function is constant in between -1 to 1. So this sinc function will become decreasing and decreasing and decreasing at the infinite of time. Okay, so if you put the value at x is equal to 1, okay, if you put the value at x is equal to 1, then sine pi is also 0. So here it comes to +1 and here comes to -1. If you put x is equal to 2, then also sine 2 pi is 0. So here it will become 0, and here if you put a -2, then here also it will become 0. If you put 3, then also it will become 0 in that way, 3 minus 3. So you can write one thing. I write here like sinc x is equal to 1 only when x is equal to 0, and it will be 0 if x is equal to +-1 comma +-2 comma ... Okay, so max of sinc x is 1, no doubtly. So in that way you can do the analysis of a rectangular pulse. So the basic thing is that in communication system you have to memorize one thing, like this a rect small t by tau. The Fourier transform of this rectangular pulse is a tau sinc f tau. Okay, so like in previous you see here, okay, we have to conclude this thing. So in this you do same analysis by using a tau sinc f tau. I use a different color here. For sinc f tau, I do the same analysis for sinc f tau. So sinc f tau is equal to 1 only when f is equal to 0, and it will become 0 when, I make a semicolon here, when f tau. At that place what you can do, you simply x is equal to +-1 +-2. Here f tau is there inside the sinc function, there is a f tau. So f tau is equal to +-1 comma +-2 comma plus minus 3 comma dot dot dot, so that if you find the value of f, at what value of f this a tau sinc f tau will become 0. So you will find here the value of f is equal to plus minus 1 by tau comma plus minus 2 by tau comma plus minus 3 by tau. So what you can find, you simply find that there is a rectangular pulse. Take a pen, I take a different color. Okay, so there is a rectangular pulse in time domain. Width is minus tau by 2 to tau by 2. It is in time domain signal, and here it is a x of t time domain signal, and the magnitude is a. So basically the Fourier transform of this rectangular pulse is, this is one is the Fourier transform. So the Fourier transform of this rectangular pulse is, I have to write a one straight line curve. Okay. Okay. I have to use a pen. Okay. So the Fourier transform of this rectangular pulse is x of f, and the same thing this one is not proper drawn. If you do in pen and paper, then it will be good. So here it is a frequency in f domain. Here it is a 0, and I use a different color like red. So the so at what frequencies this will be 0? At 1 by tau and minus 1 by tau, and another one is the 2 by tau, and this one is the minus 2 by tau. In that way you can find the spectrum, and here the amplitude is a tau, because if you put the here its amplitude is 1, so you got 1. Here its amplitude is a tau, so you got a tau. Or simply you can prove by putting frequency f is equal to 0, then applying L'Hospital rule. After applying the L'Hospital rule, you simply find the maximum amplitude at frequency f is equal to 0. So what you can understand that the given time domain signal xt, that is a rectangular pulse, contain all the frequency component from minus infinite to plus infinite. You can see you got a sinc pulse. So what you can understand, there is a rectangular pulse, in time domain. If you find what are the frequency component present in that rectangular pulse, you simply know that by using the Fourier transform, there is an infinite number of the frequency component that is present in between minus infinite to plus infinite. So one thing is more, what is the bandwidth? So actually practical existence of frequency is only positive frequencies. There is no significance of the negative frequency. So if you see a bandwidth, the bandwidth of this signal is lower at 0 to what are the upper frequency. So this one is the bandwidth. So bandwidth is like signal bandwidth is, so signal is xt, so the bandwidth of the signal xt is, I write here, signal bandwidth of this rectangular pulse is highest positive frequency, highest positive minus lowest positive frequency. Means if you see, highest positive frequency is no doubt infinite, and lowest positive frequency is 0. So the signal xt, the bandwidth of signal xt is infinite. one thing you have to mind, there is no practical significance of the negative frequencies. So for proper transmission of the above signals, you have to require a channel bandwidth. That bandwidth should be infinite. So if you transmit a signal xt, that is rectangular pulse, then you have to use infinite channel bandwidth, then this signal should be transmitted. But what happened, like there is a limited bandwidth available. You have not a infinite bandwidth available in the in any system. So but practical bandwidth is finite. So what you can do, then how you can transmit this signal into this signal by a channel, this xt signal by a channel, then definitely you have to limit the bandwidth. You have to limit the bandwidth. So before transmitting the signal, there is a band limiting process. So to band limit a signal, only significant so that only significant frequency component should be retained and insignificant frequency component can be eliminated. Here you can see there is a maximum amplitude in lower frequency range. In upper frequency range there is a less magnitude. So only significant component that you have to attain by using band limiting process. So significant frequency contain only 95 to 99% of the total strength of the signal. What are the total strength of the signal? That is totally distributed between minus infinite to infinite. But if you band limit the signal, 95 to 99% of the total significant frequency component you have to attain. So in that way, by using band limiting process, you have to band limit the signal. After band limiting the signal, you transmit by using a channel. Okay. So how to band limit this signal? You simply pass this signal into low pass filter. Okay. So if you pass this signal by using low pass filter, then what you can get? You simply get a significant frequency component. What are the significant frequency component? The significant frequency component is f, that is one lobe. Here you can get from here to here. So by using proper low pass filter, or simply you can get this is 1 by tau 2 minus 1 by tau. Then what is this? What is the signal bandwidth at that point after passing the low pass filter? So here signal bandwidth is highest positive frequency minus lowest positive frequency. So 1 by tau minus 0, you can get 1 by tau. So by using band limiting process, simply you can get a less bandwidth. So by using this thing, oh okay, one more thing, how this x of f can get like this one. So I want to tell you here one thing, like if you assume this low pass filter Fourier transform is h of f. So what is the ideal low pass filter looks like this. You select a bandwidth of this Fourier transform is 1 by tau, 0 to 1 by tau. So ideal, and here the magnitude is 1. If I took a magnitude 1, here it is a tau, here it is anything. Let us assume y of f, no doubt, y of f. So what is the y of f? If this x of f is passed through a low pass filter, then you know the basic property, like y of f is simply x of f multiplied by h of f. Okay, so between minus infinite to minus 1 by tau, there is some frequency, there is some strength of the signal present here, but here it is 0. So after multiplying this thing, it will become 0. And after 1 by tau to infinite, after 1 by tau to infinite, there is a some strength, but in low pass filter there is a 1 by tau to infinite, there is a no strength of that signal, so you can get 0. So by using this thing, by using proper low pass filter, you can simply band limit the signal, band limit the frequency component of the signal. So in that way you can pass through a proper channel. Okay, let's do one thing, let's do one more thing. Some properties of the Fourier transform. This is the important thing. I have to add some new pages. Okay, so let's find the some properties of Fourier transform. Okay, so the first property is, I write a different color, duality property. So what the duality property says? Duality property says if any signal in time domain xt, that Fourier transform is x of f. So if you put here, you can focus one thing, here it is a small xt, here I write a Fourier transform by using capital X of f. So if you write capital X of t here, then here it will become x of minus f. This is f. In that way, this is the duality property. Okay, I didn't prove that property. You simply refer any standard book and see the solution. This is very easy. For the communication system purpose, only I teach this thing. So what you can see by using these applications, like I saw just a previous one, like if there is a minus tau by 2 to tau by 2 in time domain signal, its amplitude is a. Just I saw one thing, there is a xt, its Fourier transform is what? Its Fourier transform is, this is a rect small t by tau. What the Fourier transform is? Sync pulse. I write a straight line. So what you see here, at that point, this one is 0, this one is the a tau, and this one is the x of f. And you see in previous just a couple of minutes, the Fourier transform of this rectangular pulse is a tau sync f tau. And what are these values? What are the frequency at which this sync pulse is 0? This is 1 by tau, this one is 2 by tau, this one is the minus 1 by tau, and this one is the minus 2 by tau. Okay, so what the duality property says? If you take this thing in time domain, then it will become just negative. So by applying duality property, is there anything like to copy paste? I think this is cut option. So if you take this thing into this side, okay, I write in proper manner. This one is the time domain, okay, and this one is the capital X of t. You see here, same thing, capital X of t, and okay, so this one is the 0, this one is the 1 by tau, this one is the 2 by tau, this one is the minus 1 by tau, this one is the 2 by tau. So what you can see here at that place, in frequency domain this should be shifted, but it is a even signal. You can see here it is a even signal. If you flip this signal, like if you put the x of minus t, x of minus, oh, not in that place, okay, you see here, this is the, okay, so here if you put the x of small x of minus f, if you put the small x of minus f, simply you have to flip the signal by vertical axis. So here you can see at that place, this one, it is in frequency domain. So this one is the minus tau by 2 to tau by 2. So by using duality property, you can see this thing. If there is a rectangular pulse in time domain, the Fourier transform of this rectangular pulse is sinc pulse. If you take out the sinc pulse in that side, then this thing will become this side. So the Fourier transform of this capital X of t is small x of minus f, and no doubt here its amplitude is a, and here its amplitude is a tau. There is no change in the amplitude. Okay, this thing will be helpful in the in upcoming session, like at that place where you see like there is a, to avoid the ISI, intersymbol interference. You see here one thing, like if you transmit a signal, if there is a rectangular pulse you have to transmit, then there is an infinite, it demands an infinite amount of the channel bandwidth. So there is a, so better way is, instead of transmitting a rectangular pulse, you have to you transmit a sinc pulse. If you transmit a sinc pulse, then the bandwidth is less. Here you can see the bandwidth is less, bandwidth is only tau by 2, but what at in that place, here it demands a high bandwidth. And here if you transmit a time domain signal in that way, sinc pulse, then it demands a less bandwidth. Here you see the bandwidth is only a here the signal bandwidth is only a highest positive frequency minus lowest positive frequency, so this will become tau by 2. So by using simple analogy, I have to do one more thing, like a bit of ISI. That thing we have to study it in upcoming sessions. Like if there is a sinc pulse in that way, oh, this thing is not right. Okay, I put a same thing, like here this will become, it is in time domain signal. So the Fourier transform of this thing is simple rectangular pulse. This is the, it is in frequency domain. Okay, here it is x of f, here it is x of t. I told you, like if your signal is a rectangular signal, then it demands a high channel bandwidth. But if you transmit a bandwidth of, if you transmit a sinc pulse instead of rectangular pulse, so I put a here at place of tau by 2 I put a 1 by RB. What is the RB? What are the different things? We see upcoming session. Here it is minus 1 by RB. Here it is minus 2 by RB. So what you can see? Simple analogy. Here if it is 1 by tau, then here it is tau by 2. Here it is 1 by RB, then no doubt here it is RB by 2. Here it is minus RB by 2. So you have to simply focus on, not focus on at that point. I will teach this thing in the upcoming session. So basically the thing is that by using this thing you can simply avoid ISI, inter-symbol interference. I will teach you this thing in the next session, next 1 to 2 session. Okay, so okay, so there is some more functions that you have to know, like I have to take a pen. Okay, the Fourier transform of the impulse signal is 1. Okay, so what is the impulse? Impulse is a simply del t. Its magnitude is infinite, where at t is equal to 0 and its magnitude is 0 otherwise. So basically impulse function looks like this. At t is equal to 0, here it's not t is not equal to infinite. I have write wrong. Here also it's t is not equal to 0. Only at t is equal to 0 its magnitude is infinite and area is 1, and other than t is equal to 0 its magnitude is 0. This one is the impulse. Here it's 1, so its area is 1. You see here its area is 1, but no doubtly its magnitude is infinite. Okay, so one more thing is that this impulse signal minus infinite to infinite del t, if you take the area, then no doubtly area is 1. One more thing is that I write here, if I put here a del t, let us assume I put here a del t, then definitely minus infinite to infinite a del t dt, then its magnitude is no doubt infinite, but its area is a. You have to notice one thing. So by using this thing you have to know the duality property. I assume this thing is xt and this one is the x of f. So what the duality property says, if these things come to left hand side and these things come to right hand side, then 1 goes to del of minus f, and also the impulse function is an even function, so there is a del of f. So what you can see, the Fourier transform of f, no, so the Fourier transform of the constant function 1 is simply impulse. So if you plot a 1 means there is a constant. This is in a time domain signal. Here I can write time domain signal, time domain. This one is the x of t, it is a constant. Then the Fourier transform is, this signal is simply an impulse signal with area 1, magnitude infinite, with respect to f, here with respect to t, here with respect to x of f. So here you can also notice one thing, if there is a DC signal, one is a constant signal, DC signal. So what is the frequency of DC signal is 0. Here it's proof. The next property I want to tell you, that is the second property is frequency shifting property. Okay, so what the frequency shifting property says? Frequency shifting property says, like, if there is a signal xt, its Fourier transform is x of f, then xt e raised to the power j 2 pi f naught t is simply x of f minus f naught. And if there is a xt e raised to the power minus j 2 pi f naught t, then the Fourier transform of this one is the x of f plus f naught. Okay, so means here what happened? Here simply delayed by f naught, delayed by f naught. Here what happened? Here simply advanced by f naught. Okay, so you can see here, if xt is multiplied by a complex exponential, you can see here xt is simply multiplied by a, this one is the complex exponential, this xt is multiplied by a complex exponential function, then spectrum will shift, then that spectrum, like this spectrum, no, that spectrum x of f will shift left or right. Okay, so by using that property, simply I want to prove some of the formulas. The first thing, you know that the Fourier transform of the DC signal is impulse function del of f, you know. So if you put 1 into e raised to the power j 2 pi f naught t, so it's simply del of f minus f naught. There is a 1 into e raised to the power minus j 2 pi f naught t, then it will become simply del of f plus f naught. And one more property is that in Fourier transform is there is a additive, like it follows superposition, means addition and multiplication. So if you add the left hand side, then its spectrum will also added. If you add in time domain, then its spectrum is also added in frequency domain. So if you add this one, e raised to the power j 2 pi f naught t plus e raised to the power minus j 2 pi f naught t, then its spectrum will also added. Delta of f minus f naught plus what is delta of f plus f naught. And there is one more property, like multiplication property. If you multiply 1 by 2, then the whole spectrum will also multiply by 1 by 2, and this one is the spectrum. And what is this thing? This thing is simply cos of 2 pi f naught t. This is the formula of cos 2 pi f naught t. So the formula, the spectrum of the cos signal is two impulse signal. One more thing that I want to add in this thing, I don't want to write again and again, so I write by using different color. If you multiply by a, then no doubt here it becomes to be a by 2, and this thing is in place of a 1, this thing is a. So in place of 1 by 2, multiplication of 1 by 2, you simply multiply a by 2, then its spectrum is also multiplied a by 2. So what you see here, you simply see that the spectrum of the cosine pulse is, the spectrum of the cosine signal is you got two impulses at one of is at that point, another one is at that point. Here the spectrum of x of f, here this one is the f naught and this one is the minus f naught frequency. Here you see one thing, here delta of f minus f naught, so this impulse is present at f naught, and what is its area, a by 2, and another spectrum is present at f naught minus f naught, so here also it's a by 2. So here we see that practical existence is only left half of the side, no, right half of the side, because negative frequencies practically doesn't exist. But one thing you have to mind in this, like for energy and power, both negative and positive frequencies you have to consider. Only for energy and power I mentioned here, where is that pen? Okay, for red color pen. Okay, here I mentioned for energy and power you have to consider both negative and positive frequencies, negative and positive frequencies. But there is a practical existence in the only positive frequencies. Bandwidth, if you calculate the bandwidth, I have right here, but if you calculate the bandwidth, signal bandwidth, then you have to consider only positive frequencies. This thing you have to remember. Okay, so at the end the last property is modulation property. The third one is the modulation property. So what the modulation property says, I use a different color. So there is a xt, if there is a signal xt, its Fourier transform is x of f. Then if you simply do xt, and one more thing in previous question, what is that, yeah, in that way, in that there is a if you simply subtract this thing, if you simply subtract this thing and divide by 2j, then you get a sine formula, because e raised to the power j 2 pi f naught t minus e raised to the power minus j 2 pi f naught t divided by 2j, this will give the sine formula. So by using the same thing, you can do for the sine analysis, for the sine function, you can find the spectrum of the sine function. So the next thing is that here there is a xt. Okay, we have to see here, if the time domain signal is xt and the spectrum of this xt is x of f, then if there is a xt cos of 2 pi f naught t, then the Fourier transform of this signal is x of f minus f naught plus x of f plus f naught divided by 2. So basically I told in the first lecture what is the need of modulation. Then basically to reduce the antenna height, we have to require a modulation technique. Modulation, we have to record the modulation. So what are the concept of the modulation? Simply we saw in the last class, like I told you once again, like if there is a message signal, let us assume if there is a message signal mt, that is the rectangular pulse. This one is the minus minus tau by 2 to tau by 2. If there is a message signal x of t, its amplitude is 1. I have to assume this amplitude is 1. So this is the message signal. Okay, so if you do one thing, if you do simply, if you find the spectrum of this thing, you simply okay, I band limit this signal, after the band limiting you find the spectrum of this signal is this thing here, 1 by tau 2 minus 1 by tau, here it is a x of f. Okay, so here it's 1. So you see here, because it is a less frequency, maybe it will be 1 kilohertz. Okay, maybe it will be 1 kilohertz, maybe it will be 1 megahertz. Okay, so this type of the signal we called as a low pass signal. This type of the signal we called as a, I write a different color. So this type of the signal we called a low pass signal, low pass signal, or simply baseband signal, or simply baseband signal. Okay, means if the signal having low frequency component, then it is called a low pass signal or baseband signal. So if you transmit this xt by using antenna, then the antenna height should be too high. I proved in a previous class, if the frequency is less, then you have to require a high antenna. Antenna height should be high, like 5 kilometer, or the height of 5 kilometer height antenna, in that way, which is not practical possible. So by using modulation technique, modulation, what the modulation can do, modulation simply shift this spectrum, here it is 0, shift this spectrum into different frequency like f0, and you took this cosine frequency f0 is too high. Like I saw one thing, like if you, I use a black pen. Okay, if you do the same thing, then here it is 0, you simply shift this spectrum at here. Okay, so this is 1 megahertz to 2 megahertz, let us assume. So this is the band pass signal. I write a red color pen. So this is a band pass signal. So antenna height, here antenna height requirement is less, here less antenna height, less antenna height, here requirement of the antenna height is less, here it is a more antenna height, more antenna height. Here you have to require a more antenna height, but here you have to require a less antenna height. So the basic purpose of the modulation is simply shift the frequency from lower frequency to higher frequency. Okay, so if any signal, if there is any signal xt, if you multiply the higher frequency of the cosine signal, higher frequency of the component of the cosine signal, then it will shift from lower frequency to higher frequency. I took one more example, like okay, if I took a carrier signal, simply here we can say carrier, like Ct is equal to AC cos of 2 pi Fc t, 2 pi Fc, here it's a Fc, and you take a Fc as a 1000 of kilohertz. or simply 1 megahertz. Then if you simply multiply st by mt, mt is same thing, mt is previous signal. Here I write a bit of the mt. Mt is simply a previous thing, like minus tau by 2 to tau by 2 with respect to t. The amplitude of this thing is 1. If you simply multiply, okay, before multiplying this thing, I want to show you one more thing. Like there is a, in time domain there is a cosine signal. Okay, digital pad there is a not the good drawing, but you have to understand. Okay, there is a cosine signal in time domain. There is a xt. Okay, not xt, you have to write a ct. Where is the eraser? What's it? Okay, it erases the whole thing. I have to use here. Okay. So here it is a ct. Okay, so you see in previous just above, like the spectrum of the cosine signal is simply an impulse at frequency fc and at frequency minus fc. And what is the amplitude? Amplitude is simply ac by 2 and minus ac by 2. Simply ac by 2 and minus ac by 2. What you can do, what the modulation property says, if this mt multiplied with ct, okay, if this okay, previously I told this thing is xt, so I have, so here also I have to write a xt. Okay, so here also I have to write a xt, so you have no confusion at that place. Here xt. Okay, so if there is a xt multiplied with cos 2 pi fc t. So what is that? Like x of f minus fc plus x of f plus fc by 2 by 2. And here one more thing is that AC is in amplitude, so here also AC. Okay, so what this property says, whatever the spectrum of that signal is simply shifted at minus fc and plus fc. So if I plot the spectrum of this signal, you can see at fc is what? fc is 1000 of kilohertz, and I took this 1 kilohertz. Signal. This 1 megahertz simply for the representation, like how to represent a low pass signal or baseband signal. What is low pass signal? If it contains a low frequency component. Low frequency component means 0 to that, 0 to, or it will be 1 megahertz or it will be 1 kilohertz, but it contains a low frequency component. If it contains a low frequency component, then you can say that signal is a low pass signal or it is a baseband signal. So I erase here the bandwidth of signal. I assumed 1 kilohertz. So okay, so it goes to from here to here, like 1001 kilohertz to 999 kilohertz, and again this thing will be here like minus of 1000, and here it will become minus 999 to minus 1000 of 1. Okay, here at anywhere it is 0, it is in frequency is in kilohertz. Okay, so what you can see, whatever the spectrum of this signal, what is the spectrum of this signal? The spectrum of this signal is simply this one, 1k to minus 1k, 1 kilohertz to minus 1 kilohertz. So whatever the spectrum of the signal, this is spectrum will shift at fc and minus fc. So in that way, because the spectrum is shifted at higher frequency, so you can say this signal is a band pass signal. Band pass signal. So and if you multiply this thing, this one is the modulated signal, this one is the modulated signal, okay. This one is the modulated signal. So what you can see here, low pass signal become band pass signal by using modulation. This low pass signal, it is a low pass signal. So by using modulation, this low pass signal become a band pass signal. This low pass signal become a band pass signal. Signal will be translated from low frequency to here. It's a here all this frequency is low frequency to higher frequencies, low frequency to higher frequencies. Signal will be translated from low frequency to higher frequencies. And if you confuse like how we can say this one is the low pass and how you can say this one is the high pass, then simply you can see here, if high frequency and low frequency ratio is greater than 1, then you can say this is a low pass signal. Like I write here, if high frequency and low frequency ratio is greater than 1, then you can say this is the low pass signal. And if the high frequency and low frequency component ratio is approximately 1, you can see if you divide 1001 by 999, then you get approximately 1, then you can say simply it is a band pass signal. So from today's lecture I ended this class, and next class we see the type of the modulation, what are the type of modulation, and like single tone modulation, multi-tone modulation, and next come to modulation techniques, what are the amplitude modulation, what are the frequency modulation, and all those things we have to discuss. So in today's lecture we simply discuss basic of the Fourier transform. Here basic of the Fourier transform, what are the Fourier transform of the rectangular pulse. Rectangular pulse Fourier transform is the sinc function. You have to memorize this formula. This formula comes again and again and again. After that, what are the signal bandwidth? Signal bandwidth is simply highest positive frequency minus the lowest positive frequency. After that, we simply seen the property of the Fourier transform. There is the duality property. After the duality property, we simply we see the constant function, the constant DC frequency of the DC signal is simply 0. And also we find some of the formulas, like what are the formula of the cosine signal, what are the formula of this sine signal. You have to prove the formula of the sine signal. And after finding all these formulas, we go to the next property, that is the modulation property. You have to memorize this thing, you have to practice again and again. There is a rectangular pulse, the Fourier transform of the rectangular pulse is sinc. But if there is a low pass signal or baseband signal, then you have to require a more antenna height, like 5 km of the antenna height. But if you convert by using the modulation technique, by using the modulation property, then this low pass signal become a band pass signal, and antenna height will become less, like 75 meter, in that way. So thank you so much. I am going to end this lecture.